I sent out just the first section of notes yesterday. Did everyone get them okay? Stephanie, CJ, something like that? Okay. And then you guys here, that's just the first half. I just didn't have time to go through the whole thing and get them out. So I'll send you, hopefully today I'll have a lot more time to work on that. I'll try to send the rest of them. We're not going to make it through everything I send you in chapter 15. We just don't have enough time left. If you remember, next week we're only going to have Monday, Tuesday, and Wednesday, Thursday, and Friday we won't have class. We have a whole week off for Thanksgiving, and then we come back after that for a little bit. And we do do some review there. I'm not going to take a whole lot of time to review, and I know some teachers do. And please give me feedback. If you really hate me just giving your review sheet and expect you to do it on your own, let me know that. But that's what I'm planning right now. So let me know if you want to do something more elaborate than that, we can. But at this point, we'll just talk about some stuff in chapter 15, and we'll just see how much we get through. So 15 point, well, the whole thing of 15 is about vector analysis. So we're going back to things we talked about as vectors way back in the beginning, and we're going to say, okay, well, how can I apply those in more situations than we have so far? And so we're going to pull a lot of things that we've talked about kind of together here, but then still talk about new stuff, which shouldn't be too surprising. The beginning of this chapter just goes through and says, okay, well, vector fields. We're going to work with vector fields. What is a vector field there? And if you don't think too hard about it, just kind of take the name for what it sounds like, you can probably write a picture of what it is. A vector field is basically going to be either a plane or it could be like a three-dimensional space there. But it's some area, some region that is full of vectors. Okay, so it's like a field full of vectors, basically. We are going to go back and have functions that describe this. So we know that if I go to any point, either on this plane or in this space, how we generate the vector from that location. But the idea is we're just going on this plane, we're going somewhere in space, and then we're computing a vector based on that point that gives us a different direction or meaning or something like that, depending on the situation. So recall here the stuff we did in vectors back in chapter 11. We remember notation for that. We talked about vector valued functions in chapter 12. We had different notation for that with more parametric. And then vector fields is kind of like building on that some more. So there's definition of vector field. Okay, we've got some region, like I said, in two-dimensional space. We're just working with it over some region. We can also do it over some 3D region, actually, or 3D space, we should say. But it is just a function that's composed of vectors there. Now, how it differs from vector valued functions. Vector valued functions, we had R of t. We basically said, okay, we're thinking about this parametric. We've got some x change in terms of t, some y change in terms of t, and there's parametric there. What this is doing is it's not introducing that variable t. It's saying, okay, well, if I go to some point in space, how do I know where to go in terms of x and y? For both the x direction and the y direction there. So what we're going to be given is some vector value function that has a vector or a function component for x and a function component for y, both of which come with x and y in them. So it'll make a lot more sense when we actually see it there. We can still use that linear combination form. The book uses that a lot, so let's put that mostly as a reminder, but component form works fine. And then for 3 dimensions, we just add the z component. If there was 4 dimensions, we just keep adding components onto that. If each of those component functions is itself continuous, the whole vector field is continuous, so that's a fairly easy explanation from that. And we'll eventually see that gradients are examples of this. But before we get to that, a little bit of reason like what does this look like and kind of why do we go back and use those there. So we'll go to vector fields. This is part of the paragraph here. Many times we use to show how motion is moving over a plane or in space. We'll look at some example. We'll have some pictures in a minute, but it's showing how things change. The first picture I have on the next page is a very, very simple one. If you just have a wheel that's fixed on some axle, center of the origin there, and it's just rotating. What this vector field could represent is where are these points kind of going? Obviously, they're connected to the wheel, so a point here isn't going to move in this direction and off the wheel, but that's kind of the direction that the velocity is headed in there. So in this case, this vector field, each little vector is kind of telling the velocity of that point and in what direction we're traveling in. Hopefully it makes sense that points closer to the origin have a much smaller magnitude than points far away. I mean, think about like blades on a fan. The middle points don't really move very far, but on the very ends of that fan, they're covering a lot more distance as they travel, and that's basically what this is showing here. The further away you are from that turning point, the longer the magnitude gets there. The one below that is a bit more complicated one. This was, I forgot the website I took it from here. There it is. I looked down the bottom there. But it's showing how velocity changes around this golf club. So as a golf club swings, they can go back and measure the resistance of different things here. It's been a while since the website terms exactly what it is. But we have color coding on this one too. We've also got this heat map aspect. And so depending on what that means, we can kind of interpret it different ways. We generally want to have low resistance and not that high resistance there. And then I found another one that I just thought was pretty entertaining. Yes, aerodynamic efficiency of a cow. Some people have too much time on their hands. There it is here. But it is a big 3D vector field of a cow. So if you stick a cow in front of a giant fan, or this is all my fluid dynamics, but there is the resistance to cow face, which is just, like I said, kind of silly. But right there, I think it's interesting that the forehead of a cow is some of the most pressure, or what was this looking at? Yeah, which is, I mean, it kind of makes sense. There's an important fact that cows need to be able to feed their babies. Got to keep those things safe, I suppose. But anyway, I just thought that was kind of funny. So feel free to read through there. There's not a whole lot about it, but like I said, some people have too much time on their hands. But that's a vector field. It has these different vectors, and they're going off in whatever direction. And in reality, there's an infinite amount of these vectors, either on this space or in this field, but we just picked some of them to go through and show. Software does it a whole lot faster than we do ourselves there. If we are asked to graph these, which once in a while we will be asked to graph a vector field, although I'll show you some technology sources that do it much faster, we're essentially just going to pick points in the region we're talking about and kind of see what happens at those points there. So we'll do 2 by hand, and then we'll look at some technology for the rest of them. Okay. So it says sketch a portion of the vector field for, and then we're given this vector, this force field for this, or this vector field function. And again, the difference between this and the vector valued functions, when we talked about vector valued functions before, it was always in terms of t, and that's not what we're working with here. We don't have this in terms of some parametric function. We're saying, okay, keep it in x and y. We're not going to introduce any other parameters for this, just those 2 values. So basically, just pick points. And note that that is a vector, so it's written in bold again, so it means it has a little vector over it. So let's just say the point 1, 1. Just totally picking points here, no real rhyme or reason right now. If we look at what the function says to do, it says the vector we get at this point is going to be negative y comma x. So since right now y is 1, we're going to have negative 1. Our x is equal to 1, so our second component will be 1 as well. And then what that means, or what that looks like, is at that point, 1, 1, we're just basically going to apply this vector, or do this vector. And so if you remember what vectors tell us, it means in the x direction, we're going to go backwards 1, in the y direction, up 1, and so we've got this vector right here. That's it. That's all that means. We'll pick a few more points, kind of see what happens with this. And depending on the points you pick, you may see some kind of neat patterns. Like I said, eventually we'll just do a technology to kind of get a better overall view of what's going on there. But when I did it, I've done this a few different times. You can go down and pick some kind of symmetric points. So let's say we go down here to the point 1, negative 1. Again, apply the same function to this. We're going to have the opposite of y, so I'll make this a positive 1, and then just x, which is still 1. So from that point, we go 1 in the x direction, 1 in the y direction, and we have this thing here. And if you kept picking those symmetric points, you kind of see it makes a nice little shape. But other thing that turns out to be pretty neat is let's take a look at the point this one led to. It also makes kind of a neat pattern. So that would be looking at 2, 0. So what vector would we get out of this one? From point 2, 0, what vector is associated with that point? And so if we do 0 in the x direction, up 2 in the y direction, we get this. And let's go ahead and go from that point. Again, you don't have to do this. It just kind of makes a neat pattern in this case, so we'll continue it. So we are now at the point 2, 2. So when we apply that vector field, what vector do we get?
Negative 2, 2.
So negative 2, 2 takes us to here. And we can kind of keep going, but as soon as it's going to get off the graph, so it just kind of makes this neat little like spiral shape if we kept doing this. I mean, we could be here for a long time going through and doing this. Hopefully that idea kind of makes sense. We could very easily have picked a point over here in the negative direction. I just didn't pick one of those yet. So let's plug one of those in there to make sure our notes kind of cover all of our bases. So that is negative 2, 1. So what vector is associated with that point based on this vector field? So negative 1 in the x, negative 2 in the y, and you go up down here. I mean, this isn't difficult. It just takes a long time to kind of see what's going on with this. Just kind of keep building. Yes, Russell, thinking about it.
So why? Oh, I guess it doesn't matter. Why is it flipping?
That's just what this vector field. So when we take the opposite of y, it always just kind of flips it around there.
I mean, like it goes x, y, and then the order is y, x. They're just functions.
Yeah, it's just a random function. Yeah. So like if you look on the next one here, the function is just something different. This is just the example that I picked to go back and graph here. We'll come back to this in just a minute after we do one more by hand. I'll show you the website where you can kind of see it all at once there. But yeah, the fact that this is negative yx really means nothing. It's just random functions put in there. Yeah, it's kind of weird. All the numbers are the same, so I kept picking ones to work with. This one's a little different, so still same idea here, but now our function is 2x times y, so it'll be a little more in line. And feel free to just pick points on your own, but if we kind of jump around and pick a few points here, we'll do things that have different x coordinates and y coordinates this time, hopefully keep it a little more clear. So if we go to the point 2, 0, vector associated that was 2 times 2, so 4, and the y value is still 0. So if we graph that vector, 1, 2, 3, 4, my graph's not really long enough. I'm gonna put this. Why don't you guys pick another point? We'll do like 2 or 3 more of these. Russell, give me a point.
Negative 3, 1.
Negative 3, 1. So what vector would be associated with that?
Negative 6.
So 1, 2, 3, 1. Negative 6. I definitely should put a burger plot on here. 1, 2, 3, 4, 5, 6. I know most of you are muted, but let's say TJ, give me another point.
2, 2.
Sounds good. So that would be what vector associated with that. 2 times 2 is 4, and 2. So if we graph that guy, 1, 2, 3, 4, 1, 2. Okay, and again, you just keep doing this. There's no real rhyme or reason for doing it by hand. Like I mentioned in the previous page, unless I say do specific points, you're just picking whatever points you want to work with and just graphing vectors. And you can keep doing this for a very long time there. Okay. But the idea is that every single point on this plane has that vector associated with it, and it depends on where that point is. At this point, this vector field really means nothing. It's just some random functions that are kind of stuck together here. We very well could have had some more complicated vector field where maybe the components depend on both x and y, or one of them was constant or something like that. I mean, there's no real restrictions on what happens here. It's just kind of two that kind of got put to place. But like I said, this kind of takes a long time to do by hand. It's not really efficient to stand there and graph a whole bunch of things by hand there. There are tons of websites who would do this for you. I mean, I've just listed one of them that's pretty neat and clean. We haven't really used WinPlot as much this semester as I've used last semester or other semesters because we have better ways of graphing things. But WinPlot is like an old program that's free that does a whole lot of stuff. It is a very useful program there. So I won't really get into it too much there, but it is free to download. If you're curious about it, feel free to ask and I'll send you a link to it. It does a lot of stuff. It's just not really very pretty anymore. But anyway, that website still looks nice. There's my cow. So this thing here, okay, there's an example of a vector field. It does expect it to be in that standard linear form there, so we have the I and the J with this. But if we go back and look at the two that we were just working with, the first one we did was negative yx. So there's that example one, we graphed that vector field. There's a more detailed version of it there. But you can see kind of the same ideas. We're kind of traveling in the directions on this. If we do the one that we just graphed, what was that, 2x and y? Okay, so there's a much negative, that's why it should be negative. There we go, that matches up what we were doing better. Okay, so we can see everything's just kind of jumping out from the origin there, and you can just go through and do this. This is a way more efficient way than doing it by hand. So hopefully after doing it by hand, you kind of understand what all these points mean, but in reality, it's silly to do this by hand. Software does it a whole lot faster for us. Okay. And this may not be your favorite one. Feel free to look around at others, but it's a fairly easy one to go back and use. You can change some settings and things like that. Okay. So vector fields. So what good are vector fields? Well, like we said, they are useful in various situations to show how wind pressure is applying to things, or how fluid is acting as it moves around things, especially if you think like in the 3D sense there, you know, our silly cow or something like that. But what we're going to do from a math point of view is we're going to say, okay, well, what meaning does this have here? We said that our vector field, go back to this here, all the way over here on page 1. Okay. We said vector fields are really just some function in terms of x and y that tells us to change in the x direction, some function in terms of x and y tells us to change in the y direction. Think back to gradients. We talked about gradients in the last chapter. What is a gradient? Do you remember?
It's the easiest way down a slope. Or up a slope?
Yes, we went through and found, we were to find mins and maxes this. We were saying, okay, the gradient tells you the direction of the steepest ascent or descent, right? How did you calculate the gradient? What do we do to find it? And so if we think about what that tells us, partial respect to x, that's a function that involves x and y. That tells us about the change in the x direction, right? And the partial respect to y is a function possibly of x and y. That's what's changed in the y direction. So really, that was a vector field we were creating. We didn't use that term back then. When we go through and find a gradient, we are doing the same thing this thing is defining up here. We're just finding a vector field. And that's going to be a lot of the application that we see with this is we're going to say, okay, if we're working with gradients, we are really just working with vector fields. So let's focus on those. Okay, we've dealt with them a little bit. We know a little bit about them. That's where we go back to. The deal is, though, not every vector field is going to be a gradient. So every gradient is a vector field, but not every vector field can be a gradient. What makes a gradient special is it came from original function. It is partial derivatives, like you said, right? We're not guaranteed that if we have a vector field, just like the first two examples we did, that we can work backwards and find that original function there. And so that brings us to the idea of a conservative vector field. A conservative vector field is one that basically is a gradient. Is we can think about that vector field we're given as the partial respect to x and the partial respect to y, and then the question we're going to try to answer is, well, work backwards of what was that original function? What is this the gradient field of there? A couple other things work out here, which is why we're going to do some examples with this, but yeah, every gradient is a vector field. Working the other way around doesn't happen, so we're eventually going to have to check for that in just a minute. But example 3 says, sketch the gradient vector field, another vector field, and we'll just use technology to sketch the general thing. But specifically what we're going to go back and look at is what happens at several contours. Do you remember what we mean by saying contours? It's been a while since we talked about that. We also said they could be called level curves. Does that help any? That's fine, you're honest.
You follow lines that you choose?
Yeah, like topographical maps, that's what this thing was. We said, okay, if we want to force this function to have an output of 1. Talk about traces. Traces is another word that kind of matches up with this idea here too. Okay, if we say, okay, we want to force this function to have an output of 1, what is x and y function going to look like? If we want to force the output to be 2, what is that going to look like there? And I forget exactly what section it's in, or I'd flip back to it. But we went through and we were able to say, okay, x squared plus y squared right now is a 3-dimensional graph. It's a, be a, whatever, a sphere. I don't know what I'm trying to say here. No, it wouldn't be a sphere. Anyway, it'd be a circle, right? A cylindrical surface. But we're looking at traces for this. Anyway, here's what I'm trying to say. Let's look at the vector field. We'll use our little program to do that for us. So x squared. Oops, wrong button. That is not what I wanted to do. See if that makes a difference. Why is this graphing so awkward? Oops, times x. Oh, thank you. I don't really know what this is doing.
Did you find a gradient first?
Oh, you're so smart. Yeah.
So
Those are the kind of things that you say I do on purpose.
2x plus 2y.
Thank you. So yes, we definitely need the gradient of this guy. The 2x, 2y. There we go. Very key step to miss there. Okay, so if we graph that vector field, now that I have a vector field actually. Let's, oops, I'm typing wrong still. 2y goes over here. 2x. There we go. Okay, that's better. Okay, so there's a vector field. Thank you for pointing that out there. All right, but really what we're going to look at specifically for this problem, we're going to say, okay, well, let's pick a level curve, pick a contour, and kind of see what happens with that there. So let's say we want to force the output to equal 1. Okay, we want to force f of x. Let's use the notation that Matt uses up here too. So f of x, y equal 1. What shape would that give us? Yeah, circle with a radius of 1, fairly simple. So let's sketch that over here. It's not a very good circle, but good enough. If we pick just a few points on here to graph the vector field of, let's say we pick the point 1, 0. What vector does that point generate?
1, 0 is 1, 0.
We'll apply the vector field that I forgot to calculate before. Apply that vector field, 2x, 2y to this. We're going to have 2, 0. So go back and graph that then. Okay. We could pick a whole bunch. Let's pick one, a little more complicated one. A point that's not on an axis for this would be square root of 2 over square root of 2. So let's use that guy. And if you think about trig, that should kind of make sense where that comes from. If we apply that point, 2 times root 2 over 2 is just square root of 2. And then the other guy is also square root of 2. So that's about 1 and a little bit. So from here, if we go 1 and a little bit, 1 and a little bit, it kind of takes us to this point over here. And we can kind of keep picking a bunch of these. I'm not going to go through into the calculations, but if we pick any of the points that are on the origin, we're going to get in that same direction going to. And there's an infinite amount of points we can pick here. Okay, but we've got this here. Right? Let's pick another level curve. Let's say we want f of x, y to equal, and I know 2 would be a good next one to keep those same steps here, but something with a radius of square root of 2 is kind of messy. So let's go to, we'll say 9. That way we get another nice, easy shape to graph there. So if we force the outputs equal 9 during that level curve, we're going to have x squared plus y squared equals 9, so a circle with a radius of 3. Go ahead and graph this in different colors. 1, 2, 3. Again, not a very pretty circle, but close enough. And we'll do the same thing for a couple points here. So let's just pick some easy ones. So there's an easy point right there, the point 3, 0. If we apply, because this whole thing is still the same vector field, so it doesn't really matter what contour I'm on, it's all still in the same vector field. So I'm still going to apply that 2x, 2y to this. So if I apply it to the point 3, 0, we're going to get the point 6, 0. And yes, I know my graph is nowhere near big enough for that, but there is a reason for all this here. So let's just kind of extend it a little bit. 1, 2, 3, 4, 5, 6, way out here. Okay. And we can go through and keep picking these guys there. I mean, I want my graph a whole bunch, but we can go through and keep picking a whole bunch of these. Let's take a look at just one more. I won't graph it. Let's say 3 square root of 2 over 2. And itself again. And I won't graph that one just because I don't really have a lot of room. But we can go through and keep doing this, right? And we can pick more curves and keep doing this forever. So here's kind of the neat thing that happens when we go through and do this. If we consider all the vectors that are on one of these level curves. So let's just look at the ones that are graphed in black for now. Okay, so all of these are on the one level curve when z equals 0. Oh, I'm sorry, when z equals 1. Okay, something nice happens with all of these vectors here. Do you notice anything about those vectors? And it's not an obvious thing, but if you think about it a little bit, it may make sense. Do you notice anything about those black vectors?
We're all touching that circle.
Both these things are true, so they are all touching that circle. We kind of generated it to be that way. We force these points to be on that circle there. The reason they end up touching the other circle is just because I picked 3. I could have picked something else that would have changed that. Well, I'll kind of point you in the direction I'm going for. Do all those black vectors point in the same direction? No. No, so they have different directions there. What's the magnitude of those vectors? At least for easy ones. So like, what's the magnitude of this vector down here? It's 2. It's just 2 units in the one direction. If we look at this guy, is also easy. That guy also has a magnitude of 2. Let's go back and check the other one. It's not quite as easy to just count there. So if we find the magnitude of this one, sorry, I'm writing all sorts of wrong symbols. It also turns out to be 2. Okay, and that is the thing that happens here. So when they're on that same contour, on that same level curve, at that same value of this function here, all of the vectors, no matter what direction they point in, all of the vectors are going to have the same magnitude. So it's kind of neat too. And the same thing would work out down there with the purple ones we graphed in 6. Let's fill this out. So when f of x, y equals 1, all vectors that touch the level curve, like CJ said, or let's, instead of using the word touch, let's be a little more descriptive, that originate or start on the level curve. Have the same magnitude. And in that case, it happens to be 2. Okay, but if we go to a different level curve, so when we forced it to equal 9, forced the function to equal 9, okay, they still all had the same magnitude, but now the magnitude, we'll count in just a minute, but the magnitude turns out to be 6. Okay, if we think about the magnitude of this vector at 6, if you go through and calculate the magnitude of this guy down here, it also turns out to be 6. And so that's kind of what happens there. That property doesn't show up a whole lot there, but we'll reference it at some point depending on what sections we get to later on there. But it's kind of a neat thing that turns out is when you go to that specific trace or that specific slice of the function, all of the vector fields, again, all the vectors that are generated from that function on that vector field are going to have the same magnitude. So kind of a neat little feature there. But back to really what we want to know. If this vector field is coming from a gradient, we want to be able to work backwards to find out what the original function was. Okay, so we're first going to say, okay, well, let's check and see if we should even bother doing this work there. If we're going to go through and try to find the original function was, but one doesn't exist, it'd be nice to know that beforehand and not have to go through and do it. So we're going to try to find a way to see if we can identify if something is a conservative vector field. A conservative vector field, what it says here, there exists a differential function f such that the vector field equals a gradient. But basically what a conservative vector field means is the vector field is a gradient of something. There exists some function that this thing is a gradient of. That function is called a potential function. Okay, we'll go through more of an example in just a minute. How do you suppose we're going to find this potential function? If the vector field is a gradient, it means its partial derivatives, we're going to basically go through and undo that partial integration process there. So we'll come back to these in just a minute here. The way we're going to work backwards is using integration. This is probably going to be the closest we get to partial integration that we ever cover. It does not call partial integration, but it's that same idea. We're just kind of going to undo that partial derivative piece that we did there. But again, before we get to that, we should check to see if we should even bother doing this. So this is a very helpful theorem. Okay, so do this part first. Okay, check to see if there's even a potential function that exists. If there's no potential function, you're just wasting your time. And sure, it's not a difficult process to go through and integrate, but the less work we have to do, the better. Okay, and there's other properties conservative vector fields will have too, as we see later on. So if we have m and n are two kind of functions here, two of our components for this, and if they both have continuous first partial derivatives r, then the vector field that is built from these guys is conservative only if the partial of an n with respect to x equals a partial of m with respect to y. It's a very simple way to go through and test this, and the reasoning for it is also very simple too, so we'll go through and look at that. Not really a proof, but the right idea for this. So here's what we're given. We're given some vector field. If it is indeed the gradient, which means it is something conservative, then we should be able to say, okay, then in that case, m is the partial with respect to x, and n is the partial with respect to y. Okay, so if that's true, this should be the case there. So let's see what happens. Do you remember what we said about second partial derivatives? Specifically the mixed partials? So like partial with respect to x and then y and then x, remember? And that's really the only thing that we're doing here. So really all this is going through and doing is saying, okay, if m is equal to the partial with respect to x, if I go through and take the partial derivative of that with respect to the other variable, which I'm basically just going to write the same thing here in just a minute, we want to make sure that that is equal to, this isn't really changing much there, that's okay, the partial of n with respect to the other variable too. So y is like the variable we haven't used yet. So these are going to be the mixed second partials. And that's really all we're trying to find to say, okay, are the mixed second partial derivatives equal? M should be the partial with respect to x, sigma with that respect to y, n should be the partial with respect to y, t without respect to x. And if they are equal, then this is conservative. If they are not, then it is not a conservative function here. Okay, we're essentially going through and checking to see if this is indeed happening. And if it's not, then no. So for example, example 4. We're given a vector field. Question is it conservative? Another way of asking that is this the gradient of something? So first of all, let's assume it is. If this is conservative, then that means this first portion here, that is the partial derivative of something with respect to x. So we're kind of questioning that right now. And then similarly, the second part of this vector field, xy, we are questioning if that is the partial of something with respect to y. Okay? And if this works out, where it turns out to be conservative, so where the second partials are equal, mixed partials are equal, then we know indeed that, yeah, these are actual gradients here. So we're going to go through and say, okay, we'll take the partial derivative of m with respect to that other variable. We're already assuming it's with respect to x, so we need to do the y part of this. So what is the partial of 2xy with respect to y? I'm sorry, what is partial of x squared y with respect to y?
X squared plus
Derivatives. Derivatives are going to decrease the exponent, so just x squared. Similarly, for n, we already are saying, well, if this is a gradient, that's already the partial with respect to y. So we need to go through and find the partial of that with respect to x. And what is the partial of xy with respect to x?
y. Or, oh,
No, you are correct. It is y. So partial of the second component with respect to x is y. And then the question is just, are these guys equal to each other? And they are obviously not equal to each other. So what that tells me is that this vector field, f, is not conservative. Okay, basically there's no way I can get this gradient from some function. There's no function that exists that's going to give me both these gradients at the same time. It just can't happen. So there's no reason to try to integrate anything here because you can't get an answer. Okay, I mean, you could try it and you'll see. I mean, we'll see the method for it in just a second. You can come back and try this one, but it's just not going to work out. So function is not conservative. Vector field is not conservative. Same question, different vector field. So go through and do the same things. M is always the first component, so in this case 2x. And again, we're questioning is that the partial derivative with respect to x of some function. Similarly, n is going to be the second component, and we want to know is that the partial with respect to y of some function. So we need to take the second partials. So partial of m with respect to y. What's the partial of 2x with respect to y?
0.
And for n, we're going to take the partial of that with respect to x, which is also 0. So since they are indeed equal this time, this is a conservative vector field. So the vector field is conservative, which means this vector field is the gradient of something. There exists some higher order function above this, where if we found a partial derivative, we would get this thing out of it. Okay? So we can find a potential function. It is the gradient of something. It is conservative. They all kind of have the same meaning there, the same consequences. All right, so then the next question is, what is that potential function there? What was the function that this thing is a gradient of? And that's like you guys said, that's where we're going to go back and just basically integrate this. So on the top of the next page, same function we just worked with. Okay, we already know it's conservative. So I'm going to note that here too. Already know f of xy is conservative from example 5. So since it's conservative, we can do our next step. So how do you suppose we're going to do this? We know that m is indeed the mixed part, or I'm sorry, is indeed the first partial with respect to x, and that is 2x. We know n is indeed the partial with respect to y. So we need to work backwards now. So we have the derivatives, we want to find the original function. We said integrate, but be more specific. Like, what are we going to integrate? Okay, so let's take m. So what are we going to do to m? We're going to integrate this with respect to x. We're basically going to undo it. If that's the partial with respect to x, we need to integrate with respect to x to undo it there. So what is the antiderivative of 2x with respect to x?
X squared.
And then plus and constant c, right?
Uh-huh.
I'm going to go ahead and call it c1. Usually I don't care about subscripts, but here I'm going to go ahead and list that. Similar for n, same problem, or same solution, I guess we're doing now. We're going to find the antiderivative of y with respect to y, because we're saying that second component is a partial with respect to y, so we need to undo that differentiation process with integration. And so the antiderivative of that is going to be 1/2 y squared plus some other constant. So with the results we have right now, remember the point you're trying to find is potential function. So what is a potential function going to be based on the math we've done so far? So what function did we start with to make sure we got both those partial derivatives? We've got pieces here, we just got to know how to put them together. Basically, yeah. I mean, you know you have to have x squared. One of your components has to be x squared to make sure you get that partial derivative, so taking those pieces. And yes, we've got some constant. Let's put that there. The other function tells us, yes, we have to have that 1/2 y squared piece plus its constant itself.
Hey, 2x or x squared?
Nope, x squared. I'm sorry. I don't know why I wrote that. X squared. Totally messed up. What happens to the constants? Should I leave them as separate? Yeah, you might as well combine them. It's just one giant constant together there. The reason why I want to kind of leave them separate for now, though, to write the actual answer, and then I'll explain it. So x squared plus 1/2 y squared plus c. The reason why I left some stuff there is to remind us that when we're doing that integration with respect to x there, that like close to going to get to partial integration, this constant here kind of is incorporating both of these terms over here, because remember, in terms of x, y is just a constant. So it's a-okay for that constant to kind of have y parts in it. We don't know them from the work that we did. That's kind of what the other thing does. And then similar here, this constant is all just in terms of y, so it's just basically going to absorb that piece over there too. So when we're talking about these constants, they kind of have those variable terms kind of tied into them. In general, you can just skip them and do the integration. Just make sure in your answer you have plus and constant c, much like we always do. But there you go. That's a potential function. Is that function a vector?
No.
No. Remember, it's just a function. We took the partial derivatives to make a vector, but this is just a function here. Okay, so just f of x, y. And how could you go back and check and make sure you have the right potential function?
Do gradients and
Exactly. Just find the partials and make sure it works out, see if we do gradient, okay? And I'm not going to require you guys to go back and do that, but we could. We can go back and double check. So there's little steps for it. Make sure it's conservative. Take the antiderivative, just basically match up the pieces. The next example is going to go through and do the same thing there, but you'll see kind of the one thing to watch out for. Same question. Find a potential function for this. If it exists, should add that piece on there. So first of all, let's check to see if it's conservative. Because if it isn't, we're just done. And we write potential function does not exist. So recall, first one is m, and we're trying to see, is that the partial with respect to x? So we need to go back and find the partial of that with respect to what? To check if it's conservative.
y.
Radio, the other piece. So the partial derivative of 2xy with respect to y, 2x. Similarly for n, we're going to try to see if n is a rate of partial with respect to y. So we need to take the second partial with respect to x, which is also 2x. So since they are equal, we know it is conservative. And again, if it's conservative, right now to us, that just means we can find a potential function. This is the gradient of something. Question now is, what's that something? So we can go back and integrate. We're going to find the antiderivative of m with respect to x. So for us, it's the antiderivative of 2xy with respect to x. What does that give us?
That is x squared y.
Mm-hmm. So the 2 and the y are constants, just kind of hang around. Antiderivative of x is x squared over 2. We're going to choose cancel. And yeah, there's plus some constant here. So if you want to write that, go for it, but it's not too imperative. We also need to find the antiderivative of n with respect to y. So undoing that partial differentiation. So in this case, antiderivative of x squared minus y dy. So what's that give us?
X squared y minus 1 plus
Mm-hmm. And then plus some constant. What do you notice about the two integrals we solved? Do they have any terms in common?
Yeah.
Yeah. Do you think we need to include that term once or twice?
Twice.
What?
Oh, wait, no, once, because you're saying the C's.
Right, yeah.
Bunch.
Okay, so we're saying the C kind of accounts for the ones that just have the other variable there. So our function here, if the term occurs more than once, we just need to make sure we pull it off once there. We're not going to have to include it twice. So we'll have x squared y minus 1/2 y squared and then plus some constant. And again, if you're not sure you pulled the right terms the right number of times, just go back and find the gradient and double check. If you go back and find the gradient of this function, you should get the same thing that we started off with there. But the point on that one is just be careful. There's times where you get the same term showing up more than once. Don't include it more than once. Okay? And it's quite possible that you'll get the same exact thing both times from this calc we did, or I guess we didn't. You could get the same exact thing both times, and that's fine. It just means that is your potential function. There's no other pieces to add to this there. Okay? So again, a lot of this stuff isn't really difficult. It's just using things we know in different regards. Okay? Oh, perfect. And there is curl of a vector, which is a good place to pause it. So next time we'll start talking about some other related things and aspects of this, and I'll get more notes worked on and sent out to you guys there. Homework for this I don't think is posted yet. I will get that up hopefully today as well. We don't really have a whole lot of assignments left since we're so close to the end of the semester there. You've got homework that is due this coming Sunday, and the test is due on Monday. We won't have a quiz next week since I canceled class on Thursday. We won't have a quiz next week, which means I guess we have no more quizzes left because I'm not going to do enough of that. But then the last two homeworks that have come up, we'll have 2 weeks to work on the next one for chapter 15 since we have the whole week off for Thanksgiving. But basically there's a test, 2 homeworks, and a final left. And that's really, or I guess 2 tests, 2 homeworks, and a final. So we are very close to the end. If you have questions, let me know.
So we are testing on 15.